Today we are going to talk about the following proposition, which is written by Professor Shin. NR equals n over star R if and only if every minimal prime ideal is a strongly prime ideal for any ring. Now, to prove this thing, we should first know that what is NR, what is n over star R, and what is minimal prime and strongly prime. And so first thing is that we should notify some notations. First, NR. What is NR? NR actually is the set of all nilpotent element of R. And n over star R is the intersection of all prime ideal of R. And we will use these notations, which is that if P is a prime ideal of R, then we will use O over P, which is the set of all the elements in R, such that AB is 0 for some B in the complement of P. And OP is the set of elements such that ARB is 0 for some B in the complement of P. And I will use this. And P is the set of elements such that AB here not equal to 0 is the lower star R. For some B in the complement of P. And this MP is the set of elements such that ARB contained in the NR for some B in the complement of P. And I will use this one. Be the set of prime ideals of R. And okay, now let's see by this definition, especially the first, this one. We know that the first thing is that all over P contains in OP, and it contains O lower P is contained in OP is contained in P. This conclusion is clear, so we are going to prove this conclusion, which means we should suppose for any A in R, in OP. By this notation, OP is the set of elements such that this is true. So I say there exists an element in the complement set such that A R B is 0. And then we notice that 0 is an element in the ideal of P, in the ideal P. And since P is prime and B is not contained in P, so the only possibility is that A is contained in P, which means that OP is a subset of P. Yeah. Second thing is that MP is contained in MP and it's contained in P. Also, this is clear. This conclusion is clear. And for this conclusion, we also can use the same strategies. For any A in MP, here, we can find an B such that ARB is contained in the lower star R. Next, we are going to state that this one is the intersection of all the prime ideals of R, which means it is a subset of all prime ideals in R. Here I need this one. The intersection is a subset of P, so we get P is not in P. Then by the property of P prime, by the definition of prime ideal, we get A is in P. So we get the conclusion is that MP is contained P. Now let's see some definitions. Strongly prime. Oh, sorry. Here. It's completely prime. Minimal prime. An ideal P of R is called minimal prime if R is prime and R contains no prime ideal of it's P, sorry. P contains no prime ideal of R. Contains no prime ideal of R. Ideals. ideal, whatever. And second, completely prime. This definition will shows up in the undergraduate education, because when we are in the undergraduate education, we always call the completely prime as prime, but actually prime is not defined as completely prime. In my eyes, completely prime is how do you say, is better than prime, which is that an ideal P of R is called completely prime if P is prime and AB contains in P implies A is in P or B is in P for any element in R. Okay. Here I forgot to say that. By the definition of minimal prime, we can know that the lower star R can be written as the intersection of minimal prime ideal. Now we know two more facts, which is that R over lower star R is semi-prime. And the semi-prime definition is that ARA contains CP. In P implies A is in P for any AB in R. That is because the lower star R, which we also call the prime radical, is a semi-prime ideal of R. Actually, this is the minimal semi-prime ideal of R. And the second thing is that if NR is an ideal of R, then this vectoring is reduced. Why? Because the nilpotent set of R over NR is 0. And the reduced means that the nilpotent set is 0. R is reduced. Okay. And I need more definitions. 3. M sexton. Actually, this is a small m. S is contained is a subset of R, and S is said to be an M system. If for any element in S, there are always an R such that ARB is contained in S. There is a fact, is this for ring, P is prime if and only if the complement of P is an M system. I'm not going to prove this. I will use this fact. Now we're going to prove this one. One to two. First, I'll assume that NR is the prime radical. Then we notice that is reduced. No. It's a semi-prime. Of R. And moreover, this is a nilpotent ideal. So we get the factoring actually is this one is semi-prime ring. And here, moreover, since the NR is an ideal of R, so the the factoring of R over NR is reduced. So here we use reduced. And then reduced means symmetric. This one is symmetric. Symmetric is that I'm going to write here. A ring R is said to be symmetric if ABC is 0 implies ACB is 0 for all ABC in R. Yeah. From here we can have the equivalence conditions. If AB is R, then then ARB is 0. Now we first show a claim. For any reduced ring, S we have this one. Yeah. P is a prime ideal of S. we have OP is the intersection of all the prime ideal of S which satisfied OP contained in Q and is the intersection of Q such that Q is a subset of P. Now we should prove two sides. For one side, I'm going to say this is A, this is B. It is clear because if Q is contained in P, which implies that R minus Q contains R minus B. Here is. Then by the definition of OP is that ARB is 0 for some B in the complement of P. So we can get immediately OP contains in A, contains in B. For another side, it's suffice to show that B is contained in OP, which means the intersection of all the prime ideal, which is a subset of P, is OP. And moreover, it suffices to show that we will use this strategy. Any element, say A, do not contained in B, then A do not contained in P. And I use this because here B is the intersection of prime ideal, so it is suffice to show that for every A is not in B, so there exists a Q in the intersection how to say this? How about this? There exists a prime ideal of S with this, such that no. The strategy is wrong. Show that for any element do not in OP, A do not in B. which means it suffices to show that every element because A is not contained in B, so A do not contains in a prime ideal which is contained in P. Another thing is that there exists a prime ideal of S with such that A is not contained in Q. And we know that if A is not in Q, A should in S minus Q, which is a M system. So I can rewrite by it suffice to show that for any element do not in OP, there exists a prime ideal satisfy this. Rewrite this is, I'm not going to say the prime ideal. I'm going to say that there exists a M system. And with this, I will say S minus P is contained in M such that A is in M. Okay, I will prove this statement. Now we let A is not contained in OP. And we let A SA be the set of power of A. Since A do not contained in OP, so A is non-zero. There is the set SA as lower A do not contains zero element. And we let T be the element or the element in S such that R can be written as this form: AT0 R X X1 AT1 X2 and Xn ATn, where Xi is contained in S minus P. And T0 Tn is larger than or equal to 0, but another is larger than 0. Here is OI. And now we let M be the union of SE and T. Then we can easily to see that our M satisfies this one. Okay. Now we are going to show that our M actually is an M system. We prove this by maybe this is subclaim. No more subclaim. Now we are going to show that if M is M system, then you see M system. Moreover, A is contained in M, which means there exists a M system such that A is contained in M, but A is not in OP, and then we proved this thing. So let's prove this is M system. Yeah. How to prove this? We use the more sophisticated condition to prove M is M system. We know that M system is defined by this one. Every AB in the M system, there exists another example, whatever. There exists a R, such that ARB is S, is contained in S. But here we are going to see that for every XY in M, I'm not going to say that there exists some S, some element in S such that X product this element Y is in M. I'm going to say that X AY is contained in M. And this is also implies that M is an M system. Now, since M is the union of two sets, so we have four cases. Case 1, X, Y are both in the SA, which means X is the power of A and Y is the power of A. And then XAY is the power of A, which means that this is contained in SA. And the SA is a subset of M. Then we are done. And second case, more complicated. If X is in SA and the Y is in T, say X is A to the N and the Y is AT0, X1, AT1, X2, and XN, ATN, where XI is in R S minus P, and T0, Tn larger than 0, another T is larger than 0, but not equal to 0. And here we subclaim that. We have this one. XAY is non-zero. Why I'm going to prove this one? Because you see, XAY is also of this form in T, but if I want to xay, here, xay is in t, I should prove that xay is non-zero. So I have the subclan, and we prove this on the contradiction. Suppose that xay is 0. Suppose that this is 0, which means that an plus 1 plus t0 x1 at1 x2 xn atn is 0. Now, as I said in here, S is a reduced ring. This means that S is symmetric. What is symmetric? Let's see. Here, if ABC is 0, then ACB is 0, which means I can, I can commute the element if those element is 0 by multiplication. So here is also the same. But I want to say is that if I let here m be the power in this element, 1 n plus 1 plus t0 plus t1 plus blah 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 tn, and we let w as this word. How to say that? Because xi is in the M system, the definition of M system is that there exists such as x1 and x2 is in S minus p. There exists y or z such that x1, z, x2 is in the M system S minus p. So for those element xi, as such that xi x1, z1, x2, z2, blah blah, zn minus 1, xn, which is contained in S minus p. Okay, by this, why we want to show that? Because here also can commute the element like a to the m x1 x2 to xn is 0, but we are not sure that whether the multiplication of this is in the M system. We are not sure, so we want to assure the last thing by adding z is contained in the M system. So we add this element z, and now we have a w, this is w, to the m is 0 because this one is 0. And since our r is reduced, AW is 0. Now we get a product, an element which do not contained in P is 0. What we will get? AW is 0. Here. Here. A product an element in R minus P is 0, then A is contained in the OP. But our assumption is that A is not contained in OP, which induced a contradiction. Yeah. So our subclaim is 2, which is that XAY is non-zero. Then by this subclaim, we get XAY is contained in T. And the T is a subset of M. Then the case 2 is done. And the case 3 is that both X and Y is contained in subset T, or X is in T but Y is in SA, sorry. The case can be done by case 2. So by this, we get M is an M system. So we prove that B is contained in OP. So by these two sides, we get OP equals to A equals to B. Okay, next. Okay, back to here. We have NR 1 to 2. We prove 1 to 2, which is that assume this one is true, and we get a reduced ideal R over N over star R. So we write down this. And by the claim, OP is A is B. So we will also have the same is true for our reduced ring R over the lower star R. First, we want to show that every minimal prime is completely prime. So for any minimal prime, we have this one. Or I can see that where R bar is R over the lower radical, prime radical. We have OP bar equals to the intersection of Q bar, which is the prime ideal of R bar. Satisfy that Q bar is in P bar. So we have this one also. MP is the intersection of all the prime ideal of R, where Q satisfies this thing. From this step, maybe you're not so understand, but let's see the definitions of OP and MP. OP is that ARB is 0 and MP is ARB is in the prime radical of R. So when we have the R over the prime radical, then A bar, R bar, B bar will be 0. So they are the same statement, but a little things to change. For OP, we have R is reduced, but for MP, we have to say that they are equal. Okay, now let's see. Another thing is that is this one. Let P be a minimal prime. Ideal of R. Then we will get this MP, which is the intersection of this Q, but our P is minimal, so the intersection just P. This is very important for our proof. Now we want to show that P is completely prime, so we let AB is contained in P. And moreover, we suppose B is not contained in P, which means B is contained in the complement of P in R. Yeah. And now, we see that AB is in P, but B is not in P. So, moreover, AB is in P, P is MP. And the MP is the element of X such that X, R, Y is contained in the lower star R, where Y is in the complement of P. So AB can be considered as this X, and Y can be considered as this B. So AB, R, B is a subset of n lower star R. That is there exists a z such that actually this is every b is contained in this one. Okay, now, but I'm not sure. I'm not sure that whether this is an element in the complement of r minus p, but we can dump this by here. So that's why I didn't write down every. I write as there exists. Why? Because our p is not in p. Our b is not in p, so there exists a b such that bzb is contained in r minus p. And here is every, so we get abzb is contained in lower star r with bzb is not contained in p. What we get? A product and element is in NP, which means A is in OP, and OP is an element. Yeah, element of is contained in OP and these two. Yeah, actually this is equal. No, A is in NP. Actually, first is that A is contained in N lower P, and then NP, and NP is P. So we done this proof by is a completely prime ideal. Okay, so this thing implies this thing, and for this thing 2 to 1 is sure, because a n over star r is the intersection of minimal prime ideal, and by the second statement every minimal is completely, so the prime radical also is the complete prime. So we have the lower star r is n lower star r. Then today we finished this proof.